Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hi, and welcome to Physics with Beth and Beth. I'm Beth. We're in AP Physics 1. This is Unit 5, Torque and Rotational Dynamics. There was one concept, a quick and easy concept I want to talk about. It's called the Parallel Axis Theorem. All right, the Parallel Axis Theorem doesn't even give you any clues what it's about, really much, but it's about moment of inertia and finding a new moment of inertia for a rigid object. So you're going to see it on your equation sheet as with a little dash above it. I like to call it new because you are looking for a new moment of inertia. And we have moment of inertia of a center at the center of mass plus md squared. Okay, and you're like, I don't even know what you're talking about. Okay, so here's the deal. Remember we talked about this moment of inertia or this rotational inertia, that it really depends on how the mass is distributed as well as its mass and its radius, or if you're talking about a rod, its length, but also how that mass is distributed. So if you take this ruler I have and we rotate it at the center, all right, and we go all the way around at the center. That's center of mass, and we have an I of center of mass. And by the way, for a rod, I have an equation here. It's 1/12 ml squared. All right, because you have part of the mass that's this distance from the axis of rotation and part over here. All right. However, if I wanted to change that and I wanted to rotate it like this all the way around, that is a different moment of inertia, and you have more mass on the farther distance from your axis of rotation. So it's actually going to be a larger number. It's harder to get this thing rotating because remember, let's back it up and talk about what moment of inertia, rotational inertia is. It's that resistance to rotate. All right, it's harder to get this thing rotating at the end than it is to get it rotating at its center of mass. And why? Because of the mass distribution. This is the same length. It's the same mass. I haven't changed rulers, but there's more mass farther away from the axis of rotation here. All right, so let's get going on that. So what does this formula mean? That is representing the moment of inertia at center of mass. Okay? Now, let's talk about what these others represent. M is just the mass of your rigid object. And that's going to be in kilograms. By the way, that's in kilograms times meters squared. All right, then D, here's D's a little tricky thing. D is not the length of your object. It's not the radius if you're dealing with a round object. It's not the length of your ruler here, your rod if you're using a ruler. D is the distance from axis of rotation. I'm going to abbreviate that AOR so I don't waste your time watching this video. Axis of rotation at center of mass to the new axis of rotation. Okay? That's what distance, and don't forget to square it. That's what D represents, okay? And that is on your equation sheet. They didn't used to have it on your equation sheet. You used to have to memorize it, so that's nice that they have it this year when they updated it. But here we go, I have a problem. I have a 15 kilogram rod with a length of 3 meters rotating at its center of mass of 1, and that moment of inertia at center of mass is 1/12 ml squared. The axis of rotation is then moved to its end, just like we did with the ruler. It was rotating in the middle, now we're moving it to the end, and it's going to rotate from the end. What is the rod's new moment of inertia? All right, so I'm going to draw this rod. It's 3 meters, so I'm going to put up here 3 meters. At first, it's moving around this axis of rotation, and then we're going to move it to this new axis of rotation. I'm going to call that new, I'm going to call that center of mass. All right, so when they do this, it's pretty obvious what formula you're using, what equation. You've only got one. So I want I new equals my moment of inertia at center of mass, also known as rotational inertia. Rotational inertia, they mean exactly the same thing. They are used interchangeably all the time. All right, so I have my formula. Okay, first of all, I got to find I center of mass. They told me the formula. Hey, your I for this rod at center of mass is 1/12 ml squared. Now, the reason I picked rod here is because we tend to use round things, so we have mr squared, but just to know with the rod, it's ml squared. All right, so I'm going to put that in, 1/12. My mass, we already said, was 15 kilogram rod. The length was 3 meters, so I'm doing 3 squared, which is 9. That's going to be that new I at center of mass, which actually happens to be 11.25 kilograms times meter squared. So I can put that in here. So that's going to be 11.25 plus my mass, which is 15. Now I got to deal with this D. Remember, D is not the length of the rod. I'm not putting in 3 squared here. It's the distance from where the axis of rotation at center of mass is to the new axis. So if this whole thing is 3, axis of rotation is always in the center, so that's at 1.5 meters from this left end. So that's the distance from new axis of rotation to where the center of mass was. It's 1.5 meters because center of mass is always in the center and then axis of rotation on the end, so it's 1.5. So it's 1.5 squared, and you're going to get new moment of inertia is 45 kilograms times meter squared. Now, I told you when we did the example, if you remember, I'm in this little demo, that hey, it's easier to spin in the center. Because look, it's moment of inertia, it was only resisting 11.25 kilograms times meter squared. So the lower the moment of inertia, the less it resists. It says, hey, yeah, let's start spinning. Let's go, let's roll. All right, the end though, I told you, hey, it's kind of harder to get this thing to move around by the end because you've got more mass farther away from axis of rotation. All right, well, sure enough, 45. Higher the moment of inertia, the more it's resisting rotating. All right, that's it for this video. If you like it, please give us a like. If you haven't subscribed, we'd love for you to do that. Please pass on our YouTube channel to peers if you find it helping, so that they can get help as well. That's what we're here for. And thank you for watching, and happy physicsing.